Good afternoon, everyone. It's my pleasure to welcome you to this webinar on energy industry scholarships available at Monash University. My name is Roger Dargaville. I'm the Deputy Director of the Monash Energy Institute. And I'd like to acknowledge the traditional owners of the land that I'm speaking to you from, which is the Wurundjeri people of the Kulin Nation. And I pay my respects to elders past and present. And I also acknowledge that people joining this virtual meeting are doing so from other traditional tribal lands, and I pay my respects to the elders of those tribes as well. Doing a PhD is a really amazing thing. You'll probably never get the opportunity in your life to spend 3 years on a single project that you lead, develop, and reap the rewards. It's an apprenticeship in research where you hone your research skills and experimental skills and become a world expert in your chosen domain. It opens up doors for your career and, of course, entitles you to put the letters DR in front of your name. It's also a really big challenge. 3 years is a long time to spend on a project, so you need to be fully committed and love what you do. So be very careful when choosing your topic and your supervisor. Today, we're presenting opportunities to do PhDs in the energy space with the Energy Scholarship, which honours the late Matt Zema, past CEO of the Australian Energy Market Operator, and the Woodside Scholarships, where you have an opportunity to work on transforming a fossil fuel company to a low carbon energy company of the future. Our speakers today will be Dr. Jenny Reisz from AEMO, who will speak about her role and how her PhD led her to work with the market operator. Vincent Makota, a recent recipient of the Zema Scholarship, and Sarah Goodwin to speak about some of the topics available for this year's Zema Scholarship. For Woodside, we have Professor Paul Webley to speak about the Woodside Monash Energy Partnership, Stephan Modest, currently pursuing his PhD with a Woodside Scholarship. And finally, we have Tanya Tan, our graduate research manager at Monash, to address some of the questions around the logistics that you may have about these scholarships. I'd like to thank Nancy van Novenhoven for her work in putting this webinar together. So thank you very much, Nancy. As we go, if you have any questions, please type them in the Q&A function in Zoom, and we'll answer those questions in due course. Okay, so let's get into our speakers. And our first speaker, as I mentioned, is Dr. Jenny Reisz, Principal at AEMO, leading work on operations and integration of renewables into Australia's grid. Jenny earned her PhD at the University of Queensland and has worked at UNSW and at Rome Consulting. So with no further ado, I'll hand it over to you, Jenny, to give your presentation. Thank you.
Thanks, Roger, and hi, everyone. Okay, so I'm going to share with you a little bit about the work that we're doing at AEMO. Particularly, I'll talk a little bit about some of the exciting things happening in my team, and then a little bit about my background and how I've got there and how a PhD has really helped me with my work. So my team at AEMO, I sit under operations, and we have responsibility for understanding how we integrate very large quantities of distributed photovoltaics, so rooftop solar panels, because rooftop PV is now possibly the biggest generator in the grid. These numbers here are showing you the percentage, the maximum percentage that we've hit of underlying customer load met by distributed photovoltaics in each region. For South Australia, you can see we've hit periods where almost 80% of the customer load in South Australia was being supplied just by people's rooftops, small scale distributed PV. Western Australia at 53% that they've hit, more than half of their power coming from rooftops, and almost 40% in Queensland and Victoria as well. So it's now a massive part of the power system, and it's having big implications for how the grid runs. So my team is responsible for understanding what does this mean for how we run the power grid, and how do we make sure that everything works smoothly with this very, very different type of power system. So just to illustrate for you what that looks like, this is that particular day on South Australia. This happened in October last year. You can see this is the underlying customer demand in South Australia, and this is the amount of it that's being met by distributed photovoltaics, an absolutely massive chunk of supply from people's rooftops. Actually, most of the rest at that time was being met by large-scale photovoltaics. So it was really South Australia fueled by the sun on that day. An entire gigawatt scale grid. So it's an extremely exciting time to be working in the power industry. We're really pioneering world first stuff on our grid right here in Australia. We've been looking at what does this look like going forwards. So this was released very recently, just Tuesday, sorry, this week. The Electricity Statement of Opportunities was released, which is our forward projection over the coming few decades of where things are going. This is looking just over the next few years at the projections for the amount of demand that will be met by distributed PV. And this is looking at the total for the NEM mainland, the whole mainland grid around Queensland, New South Wales, Victoria and South Australia. And we're projecting, we've hit periods with as much as 35% of that whole grid supplied by rooftop PV. We're projecting that growing over really just the next few years up to 70 to 80% of the power on the entire NEM mainland supplied by people's rooftops. And that means only a decreasing percentage supplied from the big generators. And the big generators are the ones that at the moment are supplying all of the system security services that we need that keep the grid stable, provide the frequency control, the voltage control, all the things that we rely on to keep the grid stable. So we have an incredible challenge ahead of us to figure out how are we going to continue to keep the grid stable whilst having fewer and fewer of those big generators online. And there are definitely ways to do that, but it's a very, very major transition and happening extremely quickly. This band here is showing you what we've calculated. So this is some of the work my team has been doing, looking at how low can it go before we start to get issues where we can't actually supply all of those grid services anymore with the current fleet that we've got. And that band is showing when we start to get into that realm. So we're talking 2024, 2025, really not far away. We've got demand levels down in the range where we're going to start to have trouble if we don't take some action very quickly. So really exciting stuff to be working on this in terms of understanding what these challenges look like, where do they lie, crunching the numbers and getting action happening around figuring out what we have to do to make this a reality. How do we actually run this grid? We also look at things like how the distributed PV is behaving in disturbances. So this is showing you some numbers from the, you might remember from the 25th of May earlier this year, there was an explosion at Callide in Queensland. And we've been doing a lot of incident investigation around what happened and how did the power system behave in that event. My team has been looking at how did the distributed PV behave, because this happened in the middle of the day. It was around 2 p.m. And there was a lot of distributed PV operating. These circles are showing you the amount of PV from a bunch. We were looking at, this is a data set of about 25,000 inverters that we're measuring right across the grid. And we looked at what they did. The blue ones rode through, showed no real response. The black ones disconnected from the grid. You can see a whole bunch of them around here, which were responding to low voltages that we saw in the network. And a bunch of them up here responding to the under-frequency load shedding that happened right around Queensland. So this is a whole new realm of work that's very much getting into the big data space around how do we actually observe what generators are doing when there's millions and millions of them across the grid, all these tiny systems. How do we get a handle on what they're doing? How do we build the tools and processes that we need to understand that? And there's a lot of work that's very much cutting edge research that's happening here. We've got a project working on this with University of New South Wales to develop those systems and tools. And a lot of this feeds into models. Model development is the other thing that my team spends a lot of time working on, because in order to understand how the grid's going to behave, we need to have accurate models. And those models now need to include distributed PV. Once we understand what it's going to do, how do we then project forward? So this is a model that one of my team members has put together for the West Australia grid, and it's replicating an event that happened on the 2nd of January early this year, where we saw a big event that caused a very significant drop in frequency. This is a major event. Frequency should normally be at 50. A power system that's at 49 hertz is a fairly sick power system. And in this event, frequency just touched that threshold and we saw a whole bunch of PV trip off. And we can use this to calibrate our models to understand how much PV trips depending on how low the frequency goes. And you can see here, there's some scenarios we were anticipating where that would have meant very dire consequences for the power system. And other scenarios we were looking at where it looked like it could be fine, just depending on the difference in the distributed PV behavior. And so we're able to calibrate our models and then understand the degree of risk that we've got on the power grid in those scenarios. So that gives you just a little taster of some of the things that me and my team are working on to try and understand how we run this grid and the actions we have to take. I guess a little bit about how I got here with the work that I'm doing. As Roger said, I started out at the University of Queensland. I did a Bachelor of Science and a PhD in the area of physics, actually. It wasn't in the energy space. But I became very passionate about addressing climate issues during my PhD. And so I took a bit of a sidestep into the energy industry because I wanted to work on 100% renewables and making that a reality. I was very lucky to get a job at Rome Consulting and spent about 6 years there learning a lot about the energy industry. Became really passionate around how we actually build market frameworks that are going to work for 100% renewables. And over that time, I became increasingly aware that we couldn't really build a market until we understood technically how that power system was going to work. And I was asking lots of questions of lots of people about, how would you build a power system that was 100% renewables? Technically, how would that function? And realized that nobody really knew. There weren't answers to that available. And so I really wanted to work on that. But when you're at a consultancy, you have to work on the questions that clients want you to work on. And there were not a lot of clients that were asking us to look at 100% renewables at that time. So I was very lucky that I was able to then step back into the academic world and do a postdoc as part of the CSIRO Future Grid project at UNSW, because I really wanted to work on these questions around 100% renewables, and I wouldn't have been able to do that if I didn't have a PhD, basically. I was able to step into that postdoc role and lead and work on the research that I felt was really important. So it was a really exciting opportunity to be at UNSW to work on those questions. So I think having a PhD really opened a lot of doors by being able to kind of step in between in industry and academia and be able to kind of work in both worlds because I'd had that experience behind me. And also meant that I was able to travel a lot. I went to a lot of conferences, built a lot of international connections, a lot of international knowledge that also really wasn't available through the work that I was doing in industry. That's very much stuff that has now, in my role at AEMO, stood me in very good stead because I know a lot of people internationally from being able to travel and attend a lot of those conferences through my time at UNSW, and really leverage the benefits of that now through the work that I do at AEMO. So I absolutely, although, as Roger said, doing a PhD is a hard slog. It is a big commitment to take on, but absolutely something that I really cherish and very much value, having had that experience. It really does deliver great benefits to me.
Fantastic,
So, over
Jenny.
to you, Roger.
Thank you very much for that. Quick question from me. Did you love your PhD? You said it's a hard slog, but did you love it? Probably not the entire time.
I loved the first half of it. I think about halfway through was when I realized that the topic I was working on was not the topic I was most passionate about solving. I really wanted to work on addressing climate change, and my PhD topic was a bit sideways to that. So I basically finished it so that I could then move on to that question that I really wanted to work on. But overall, it was a really, as you say, a really exciting time to be able to spend all of your focus working on a problem and working it through, and spending a lot of time collaborating with other researchers and so on. You never get so much freedom.
And your experience shows that you can move sideways from a PhD in one area into other areas. It doesn't lock you into a particular career path. It's more about developing the research skills that you need to tackle complex critical problems. So yeah, I've got a question in the Q&A from Ariel, who's asking, what scope is there to go back to first principles in market design and to, for example, repeat the process in the 1990s when the NEM was first designed?
Look, these days, as I said, I used to work in kind of market design. That used to be my passion. But these days, I actually really focus on just technically how we're going to make this grid work. So it's actually quite a lot of years since I've spent a lot of time thinking about the market frameworks. So I'm probably not the best person to answer. But I do think we've got a good system in the NEM. The NEM has a lot going for it as a market. Our FCAS markets have a lot going for them as well. I wouldn't throw it all out, but certainly there's some big things that we're going to have to work out to make this grid work.
The system definitely, as you showed in your presentation, is very different to what it was in the late 90s when it was developed. So yes, some big changes to happen. I've got one more question I'll ask you from Grace Tully. I'd love to know if Jenny went straight into her PhD after her BSc, or if you took a break. And do you recommend doing straight from BSc into PhD, or is taking a break a good idea?
I went straight into it. I actually extended my honours thesis and turned that into my PhD, mostly because I had a brilliant supervisor that I was really, really enjoying working with, and the topic was interesting, and so I continued on to do my PhD after that. And I also got a generous scholarship, which was very helpful and appealing. Certainly that approach worked for me. I really enjoyed it. I was in the swing of things and enjoyed continuing on, but for others a break might work. I think it's up to the individual.
Yeah, very much so. Fantastic. Thank you so much, Jenny. Okay, we'll move on to our next speaker now, which is Dr. Sarah Goodwin, who is a lecturer with the Monash Immersive Analytics Lab. She has over 15 years experience in academic and professional world with geospatial analysis, information visualization, and she's been working with AEMO on ways to optimize data displays for control room operations. Sarah got her PhD from the University of London, and she's going to be talking to us a bit more about the variety of projects that are on offer for the current Zema AEMO scholarship. So over to you, Sarah.
Hi, thank you for the excellent introduction, and thanks, Vinny, for your talk. I just wanted to start off to say my PhD topic was about energy data, and it's one of the reasons I'm excited to work in this area, and it's one of the reasons I'm still working in this area. But I didn't go straight into a PhD. I actually spent a number of years in industry first, and then did my PhD, and now I'm obviously working as an academic. So everyone's path is different. It very much, I totally agree. It very much depends on the individual. So, as Roger says, I'm a lecturer here at Monash. I work with the Faculty of IT. I work in particular about communicating complex data, all about the energy industry. I also work with lots of other academics here at Monash Energy Institute, all around the university, where we're looking to really try and focus on research problems that are relevant to the industry, and really looking to see how we can improve. One of the things I'm really excited about this scholarship, because it's promoting multidisciplinary research. We're joint between engineering, IT, and business faculties, and obviously further afield if that works for your project. We've got a website that tells you all about this particular scholarship. It's a really prestigious scholarship here at Monash. Totally all about working in focusing on an energy relevant problem. And here, obviously, it would tell you all about how to go about applying and whether you are eligible, that kind of thing. But the main thing I want to talk about here is there's a wide diversity of the types of projects that you could be working on for this scholarship. It's not focused, I mean, even if you maybe you haven't got an energy background, or maybe you've been working in energy for a long time already. So lots of these could be relevant to you, totally. It's the academics here at Monash have put forward 6 possible projects. 2 of them, for example, I can talk about. These are projects that I've put forward for this, but you're open to suggestions. Here, we're totally open for suggestions of if you think, oh, this topic needs to be answered, it's very relevant for this particular scholarship, and I've got experience in it. We're very interested to hear as well. And particularly if you know a academic who's working in that space, get in contact with them, tell them that you know of this scholarship, see if it's possible through that route. You can see there's a nice variety here of the kind of faculties and the kind of knowledge that goes into these different topics. 2 of the ones that I put forward are number 4 and 5. This links back to some work that I've been doing with AEMO. Previously, I led a research project where we were looking at the cognitive load of the control room operators. So they're electricity control room operators. They're there 24/7, a lot of data coming in, really trying to understand what it is that they're trying to make decisions based on this data, and how we can run research projects related to this and actually try and improve that process. One of them is this. One of the things that they're obviously looking at is forecasts. They have short-term and long-term forecasts, and uncertainty is of course, part of that forecast. And I'm looking at how can we improve the communication of that, both visually and through our knowledge of that data. So working with Rob Heidman and Di Cook from the Business and Economics group in the Economics faculty. And we have a long history of working in that space, both from temporal data and geographical data, uncertainty and visualization. So very excited about this project, and hopefully we'll find someone who's interested. And if you are interested, please get in touch. This second one is a completely different type of project that came out of the same research that I was working on at AEMO, where one of the interesting aspects was actually the way that their workstations are laid out can really impact on the way decisions can be made. So we're looking to try and optimize that workspace and understand where applications are located on their screen and how decisions can be made quicker and more effectively, and how the communication between operators can be improved based on the technology. So this is much more of a kind of optimization and technical project. I'm working here with Guido from Faculty of IT, but also Lee Lawrence from Monash Business School. He was involved in the previous project with me. So these are two very different projects. You can see how diverse they are, just coming from the same academic. And again, we have lots of other suggestions up here, one from Roger and Ariel, all about improving models, tools for studying large-scale electricity systems. So hopefully that gives you a bit of an understanding of the diversity of the types of projects that we're interested in. But also, as I said, we're very interested in any projects that you suggest. And certainly the two candidates that we've had so far are doing very exciting projects in this space and really benefiting from that link with the AEMO. And they're working in communication with them and really making sure that their work has an impact in industry. Hopefully I didn't forget anything.
Fantastic, Sarah. Thanks very much for that. So I can't stress enough that the breadth of topics that AEMO is interested in, and Woodside for that matter, that are interested in to solve the energy transition problem are really, really broad. And it's not just the technologies. In fact, if anything, we're probably reasonably comfortable with a lot of the technologies. The challenges are more around the peripheral. And how do we design the markets? How do we deal with the behavioral dynamics of the humans interacting with the system at all the different levels? How do the policies and the regulatory frameworks need to be altered? So, Sarah, can I ask, in terms of interacting with people at AEMO, so I mean, these scholarships will have Monash supervisors, of course, but they are addressing questions that AEMO is interested in solving. So from your experience, how does doing research with the staff at AEMO, how does that go?
Oh, it's really interesting. So certainly from the project that I was working on, we were in touch with them very regularly. And we ran a user study there. The operators were excellent, really interested to be involved, really excited about the fact that we were, ultimately trying to improve their workload, their workflow. So, generally across the board, I think everyone I spoke to were very, very helpful and very useful. We talked to the trainers, the trainers there. They, shared as much as they could, as knowledge as they could. We were there in the control room, 6 o'clock in the morning, and watched the handover between the sessions. Generally, really, really interesting. And there's nothing better to do research, in my opinion, than to actually watch the people who are actually going to use it and benefit from that research and the output that you're doing.
Great. Thanks so much, Sarah. Okay, we're going to move on. I can see there's some questions popping up in the Q&A that are more on logistics, and I'm going to save those until Tanya gives her presentation. And Glenn Drover's put in a couple of links in the chat also relating to research projects, so have a look at those if you get a chance. Okay, our next speaker is Vincent Makota, who is a current recipient of one of the Zema scholarships. So he's one of our best and brightest who got this scholarship and has been working on it for about a year. He got his bachelor's degree in electrical engineering from RMIT and is currently working with Dr. Behrouz Barani in electrical engineering at Monash on new technologies such as grid-forming inverters. So I'll hand over to you, Vincent, to give your presentation, please.
Yeah, as Roger mentioned before, I'm looking at grid-forming inverters as a grid strengthening asset. So just to give a brief introduction about me. So I went to RMIT University between 2015 and 2020 to 2019. And I received a Bachelor of Electrical Engineering with honors. During my time there, I received numerous awards. One of those was the Air Master Prize, which was awarded to the highest achieving undergraduate electrical engineering student in their penultimate year. And I also received the 2020 Electrical Engineering Award, which is similar for your final year. And I was also included on the Vice Chancellor's list of academic excellence. Between 2017 and 2021, I was at Bosch Australia, and that included a year-long full-time internship. And then in that time, I worked in research and development of vehicle access systems, which gave me my first taste of research and made me realize that I was actually very passionate about research. And during that time as well, I gained a lot of experience with systems engineering principles. So working in multidisciplinary teams and trying to apply research techniques in that area was very interesting. And my time there resulted in a patent application for my undergraduate thesis. And as of the start of this year, I've been at Monash University, and I'm the recipient for the 2021 Zema Energy Studies Scholarship. So my research area will focus on control aspects of grid-connected power electronic converters. So with these converters, you can either have a grid following inverter, which is the most widely adopted grid synchronization method at the moment, which requires what's called a PLL, or phase lock loop, to follow the grid current. But this one suffers in low SCR grids or weak systems, which would be the future power system with reduced synchronous generators. So in the future, we'll rely more on grid forming inverters, which can form the grid frequency and voltage and achieve load balance similar to synchronous generators, and they can be utilized as a grid strengthening asset. But however, they're immature in bulk power systems. So there's a lot of trials going on at the moment to research this area. So in the present power system, you have a lot of generators at the moment, not a lot of inverters, but in the future, you're going to have the opposite. So yeah, so obviously the physical inertia of the synchronous generators is desirable as it provides the system strength, but the future power system will have more inverter-based resources and less synchronous generators. So grid-forming inverters will need to be employed to provide that required strength. So in line with this, my research interests include investigating the stability issues related to this increased penetration of inverter-based resources. In particular, I'm interested in looking into the oscillations caused by the reduced inertia and the inverter control interactions. And I'm also interested in applying nonlinear control techniques to these grid-forming inverters. So with linear techniques, this might be a little bit more detailed than it needs to be, but usually use a PI controller or what's also known as a PR controller to control these inverters. And you control them in DQ domain, but the control becomes unstable during unbalanced grid conditions, and the control is also susceptible to grid frequency variations, which will be highly likely in the future power systems with reduced inertia. So one of the nonlinear techniques that's used to address this issue is applying artificial neural networks. So they have been applied in the past, and they've shown that they have high accuracy because they have the ability to map any nonlinear function. And essentially the control of these inverters is a nonlinear function. So a technique such as an artificial neural network could be very useful to control these inverters in the future. So they've shown to produce fast response, low overshoot, and better control performance, which are very, very important control parameters for control of inverters. So in this figure, you can see that this is a conventional controller. This is just a normal neural network controller, and with step changes in the reference currents, you can see that even though this has a higher resolution, this provides a much cleaner waveform, meaning that the artificial neural network based controller performs a lot better than just a conventional controller. And just to skip past some of this information, So the other idea that I'm interested in is the idea of virtual inertia. So obviously, virtual inertia is required in response to a frequency, any sort of frequency drop. In the future power system, you won't have a lot of physical inertia from synchronous generators. So grid-forming inverters will need to provide what's known as virtual inertia to minimize the nadir and to reduce this rock-off that you see. So you can do this by employing a battery energy storage system, or you can even having a capacitor, the DC link of an inverter, and you can use this to inject power in response to that frequency drop. And that power injected would essentially be the virtual inertia. But you need to take care when selecting this inertia constant, because you need to consider the trade-off between providing good frequency stability and frequency response, and also the reliability of the converters, because if you inject too much power, then there will be an overcurrent situation. So in response to that, there have been adaptive inertia techniques, which are based on heuristics. So you essentially set these constants based on the heuristics, and you don't really, so this requires engineering knowledge. You look at the frequency angular acceleration, and you use the fact that the inertia is inversely proportional to this angular acceleration, and then you utilize that to arrest that rock-off, the rate of change of frequency. And the damping coefficient is inversely proportional to the frequency deviation, and you use that to reduce the extent of the frequency nadir. Other techniques in the literature basically exploit this basic concept, but this is very difficult to do because you require good engineering knowledge of the system to actually set the constants that you need. So one of the areas that I'm currently actually looking into is how you can use a neural network to adaptively tune this inertia. Basically following the same concept, following the same relationship outlined here, but instead you'll be using a neural network to make the decision instead of setting this constants based on your own engineering knowledge. So just some of the examples of grid-forming inverters in industry. So as mentioned earlier today, following the Carlisle explosion, there was a lot of inverters that tripped out. But what Tesla was able to demonstrate was basically the behavior of this virtual inertia in grid-forming inverters. So traditionally, following a frequency disturbance, the generator would inject power in proportion to that disturbance. And what you see is the maximum power injected occurs at the nadir, whereas, and this is just a traditional inverter that's responding. And now with a grid-forming inverter, what they were able to demonstrate was they can inject the maximum power at the maximum rock-off, which is actually beneficial in terms of reducing the rock-off and the nadir as well. So yeah, that's basically what I was explaining there. And what PowerLink was able to do was they did a PSCAD assessment of grid-forming inverters. And what they were able to demonstrate was that grid-forming inverters can enhance the system strength, providing a range of services. So in here, you have undamped oscillations following a disturbance without the grid-forming inverter. And when you have a grid-forming inverter, you can have damped oscillations essentially. And also grid-forming inverters can provide similar damping performances as synchronous condensers at half the capacity. So another technique to provide system strength is use synchronous condensers, but grid-forming inverters can pretty much provide the same sort of stability at half the capacity, which is obviously good from a cost perspective. However, one of the issues, an issue with the voltage and transient stability arises when a contingency occurs between bus 1 and 2. So that's what they noted. So basically, what that means is, even though with a grid-forming inverter in the system, what PowerLink was able to show was it can solve some of these oscillations that you experience, but it is not a foolproof solution. There still needs to be some research done to investigate what some of the stability issues are and how they are related to the control interactions that happen between the grid-forming inverters and other points in the network. So that's, yeah, so that again aligns with some of my research interests, looking into those control interactions and trying to find ways to mitigate that. And some references and any questions?
Right. Thank you so much, Vincent. You've really jumped into the heart of the problem there, and you're very relevant to what Jenny was talking about at the start there with the dramatic increase in distributed PV, which will mean that there will be less coal-fired hydropower stations providing inertia. So, really important problem there. I'm going to ask you a very simple question. What does a typical day for you as a PhD student look like?
It starts very early in the morning. It usually starts with me trying to, this is what I personally do. I try to read at least some papers, at least one paper or something in the morning. Usually gets me into the mindset of what I need to do for the rest of the day. It is sort of opposite. It's kind of different to when you're working. Obviously, you don't have as many meetings or, replying to a lot of emails. So it is very, very good to just stay focused in your work. And so a typical day just includes me starting early in the morning and then just trying to work as hard as I can, get as much work as I can get done for the day, knowing that there's no distractions. And then after that, I can just enjoy myself and do whatever I want. And
by working, you're talking about computer coding? Is that the main focus of your work?
Well, yeah. So for the first 6 months, I was doing a lot of literature review, so it was a lot of reading. But at the moment, yes, I've started doing my own sort of simulation, so which involves some coding for some of the artificial intelligence work that I'm doing at the moment, and any sort of software simulations. So yeah, that's essentially what the work is.
Yeah, so a lot of data analysis, processing, coding, using software.
Yeah, definitely.
Yeah, of course. Not all PhDs are like that, but certainly a lot of engineering focused PhDs are very much in that techie space.
Yeah.
Okay, fantastic. Thank you so much, Vincent.
Thank you.
As I said in the introduction, one of our best and brightest, and his CV there is certainly very glowing. So congratulations on that, Vincent.
Thank you.
Okay, we're going to change gear just very slightly and start focusing on the Woodside Monash Energy Partnership scholarships now. And we're going to kick off with Professor Paul Webley to talk about these. So for a bit of variety, Paul got his PhD from MIT in Boston, the US, and his research focuses on the development and management of clean energy technologies, specifically on carbon capture. So over to you, Paul. Thank you.
Thank you, Roger, and I'll just bring up my screen to share. So as Roger says, I'm the director of the Monash Woodside Energy Partnership, and this is a partnership that Monash entered into with Woodside 4 or 5 years ago, and it's clearly focused on decarbonisation. So Woodside have realised as a fossil fuel company and one of Australia's major fossil fuel companies, and supplying incidentally 6% of the world's LNG, that they're not going to be able to do that in the future, and they have to go through a transition, an energy transition to a clean fuel. Incredibly difficult thing to do because of the scale that you're trying to do it at and the speed that you have to do it at. So we don't appreciate the oil and gas industry is well and truly over 100 years old, and we're trying to change it in 30 years. And that is a significant endeavor. And so we have partnered with Woodside to help them with that journey and do it really quickly. And so the way we've structured our relationship with them, it's a strategic long-term relationship with Woodside. And it's structured around three central pillars, which I've indicated on the slide. On the left-hand one is what we call new energy technologies. The central one is called carbon capture, conversion, and utilization. Those first two pillars are very much technical pillars, so they involve a lot of engineering and science work, all R&D. And then the third pillar is what we call energy leadership, which is really understanding what is the interplay of the economics, of policy, of governance, of the market in the energy transition. And of course, that's really core and underpins the technology development. It gives us the why of what we're doing. So those are the three key pillars of the relationship that we have with Woodside. And you can see some of the theme leaders within each of those pillars. Some of them are from Monash University, so you may know some of them. And it's important to emphasize that the projects we do are very closely associated with the personnel at Woodside. So we have research meetings with Woodside every week, many. And some of the folks shown there are people that we talk with almost on a daily basis. And so it's a really very close industry engagement with Woodside in order to prosecute the research program. I'd like to just show you a couple of the areas that we're working in. So this is in the new energy, and I've taken the energy leadership because it's associated with all of the work we do, and I've put it on the same slide as the other one. So this is some of the programs we're looking at in new energy. And you can imagine what is new energy. New energy is essentially hydrogen and renewables. And so, surprise, surprise, Woodside are really interested in very large-scale renewable solar PV generation, because that's going to provide the underlying energy for them to generate hydrogen for export, because hydrogen is the future fuel. So we have a lot of projects with Woodside at the moment where we're looking at all of those aspects in the supply chain. How do I build a very large-scale solar array? And Roger, you and I were involved in this literally a couple of days ago in a sprint as to try and understand what are the underlying factors involved in generating gigawatt scale solar energy at ultra low cost. And so that will spawn a series of PhD projects. How do I provide the water for electrolysis? Can I use seawater? So we have a project on seawater electrolysis. Once you make hydrogen at a very large scale, how do you transport it? Probably as a liquid initially, possibly as ammonia in the future. We have to liquefy hydrogen on a scale that dwarfs what NASA have been doing for the last 20 years. So everything is around scale. And so you can see there's some of the work there. And then, of course, to provide an underlying why and how is some of the energy leadership topics of models and simulation. What is the life cycle analysis? How can we say 1 kilogram of hydrogen has X grams of carbon dioxide associated with it? What is the models we developed to give us those answers? So those are some of the issues that we try to grapple with. The second major theme is around carbon capture and conversion. So we've got to get rid of CO2. There's going to be, even with the conversion to hydrogen, there's going to be CO2 and carbon converted. Rather than just necessarily storing that, can we actually convert that carbon to useful products, which can go into as a circular economy back into our civilization, and we can use it as maybe building products or other kinds of products. And so that's a very aggressive and part of our work that we're doing with Woodside is how do we convert CO2 into something useful? And what Stephan is going to talk about soon is some of the underlying energy leadership associated with the carbon piece. How do we actually go about proving and certifying what the carbon certificates are associated with those processes? It's one thing to convert CO2 into something else. And if in that process you release more CO2 and then finally your product becomes CO2, well, you haven't really accomplished much. So we've got to really be careful about what it is that we're doing and not chase our tail. So I won't say anything more because we're running a little bit late on time. I'm going to hand over to Roger to introduce Stephan.
Great. Thanks very much, Paul, for that excellent overview of the Woodside partnership. So as Paul said, we're going to now hear from Stephan Modest. He's a PhD candidate with the Monash Business School and the Woodside Monash Energy Partnership. And we mentioned before that not all PhDs in the energy space are on the technical side. And Stephan's a good example where he's doing his PhD on carbon neutral certificates in the Australian energy sector. So Stephan, I'll hand over to you for your presentation, please.
Thank you so much for the introduction. And hi, everyone. I'm just going to share my screen as well. Can everybody see that?
Yep, looks good.
I'm just going to say a quick thing about my background because it was quite nonlinear. And there may be some of you who have not pursued a straight academic career, and you can do that. So I actually started off after graduating from high school with, I spent about 2 years in New Zealand and South America just traveling, then pursued a Bachelor of Science at the Berlin School of Economics and Law and worked at the same time 3 years with IBM as a consultant. Afterwards went to Australia, came here on a working holiday visa for about another year, and then got a scholarship to study the Master of International Relations at ANU, where I graduated about a year and a half ago, and now I'm doing my PhD program. About 6 months in, I started in Feb this year, so I'm still quite fresh to that. I'm really involved with the partnership, the Woodside Monash Energy Partnership, in 3 ways. One way is through my PhD project. Then I also work as a research assistant with the energy leadership team leader. And I also do, I guess, a couple of side projects where I get to know different projects within the partnership. And for instance, I've worked with 2 researchers who are developing a saltwater electrolysis technology, and interviewed them and then wrote up an article about that. That was part of the reporting that the partnership did. So my PhD project is about carbon neutral certificates, and especially the climate active certification that we have here in Australia. I think at the latest time I was checking, there's about 230 companies here in Australia who have some kind of certification with the climate active organization in Australia. Those can be products, that can be the entire organization, precincts, a service, or a building. And what I'm really trying to understand is what are the different motivations in the first place for a company to become certified beyond what maybe like a business case scenario, like to what extent is this part of their, I guess, corporate social responsibility, and like what are the different kind of reasons for companies to pursue climate neutral certification? Then how is the system being implemented? Once you know that you want to go down that path and like you want to reduce your emissions, what's the best way to do that? How do you reduce your scope 1, 2, and 3 emission? And then how do you offset? And what type of marketing strategies are companies using to, once they have become certified, to promote their certification to consumers and other businesses? And then another aspect of that is what is the impact of certification on consumers? That can be like private consumers who, for instance, choose an energy plan, or who decide to go with a specific shopping company, who buy something online. Like, do they look out for certifications? What are their motivations? And what is the impact of that for businesses? Like, do they increase their sales? Do they gain market share? Do they have a better access to investments? Higher customer retention rates? So trying to understand that what comes with certifications for businesses on the one side, and also what is the impact on the environment. So like to what extent, if I reduce my CO2 emissions and then gain a bigger market share, what would be a quantified impact in terms of overall CO2 emission reduction? So that's really a couple of different aspects that I'm trying to understand with my PhD project. But as I said, I'm like still very fresh in. I'm still doing my literature review to some extent, so there can be slight changes, but this is the broad perspective. In terms of my work as a research assistant, I'm working with the energy leadership, energy theme leader of the partnership, and we are doing research on green hydrogen. So we look at what is happening in the world in the green hydrogen space, and how is green hydrogen helping our energy transition and decarbonization. So in this context, we investigate what projects are announced in which countries and regions, what is the intended purpose for the use of hydrogen. For instance, is it going to be used in transport, in industry, for export, etc.? And what are the different technologies that are being used and that are being applied, such as water electrolysis, pyrolysis, etc. There's a variety of different techniques that can be used to produce green hydrogen. We also look at the role of policymakers and different regulations that have already been introduced, and what will their impact be on, I guess, energy companies, but also businesses and consumers more broadly. And then one last aspect is looking at international partnerships that are being formed right now, and collaborations across industry more broadly. And one very interesting thing for me to see is a kind of trend or shift, one might say, that's happening right now from, I guess, a scenario where in the past companies used to do behind the door, like behind closed doors, secret research where they try to gain patents from that and then make the most money out of proprietary technologies that they've developed, to a collaboration of a lot of multinational companies right now coming together and trying to tackle the problem of climate change, and how do we decarbonize, how do we use hydrogen, and sharing their resources and sharing their know-how and their expertise in order to pursue that decarbonization studies together. So it's very interesting to see those international partnerships and research collaborations forming. And lastly, why did I decide to do a PhD? Firstly, I get to work on a project that I'm personally really passionate about, and I get to decide exactly what I want to do, which aspects to focus on, and make a personal contribution to the energy transition, not just practically, but also conceptually, I guess in a more abstract way. So as a PhD student, I think like you really feel as sort of an idea entrepreneur, and you get to develop your own ideas and your own business, and eventually make that business like develop it to such a stage where it can be used in the industry later on. So that's a really, really interesting pathway and path for me. Then another aspect is, especially in the energy transition, you're at the forefront of cutting edge technology and research. And I learned a lot about the different innovations that will eventually make it into industry, and the different processes involved in that process. You will also develop a very diverse skill set, ranging from analytical skills and critical thinking. You learn like in-depth research skills, such as how to gather and extract and process information, data collection analysis, various interviewing techniques, and of course, time management and project management skills, as you have to work very independently, set your own milestones, and meet project deadlines. So you gain a lot of these skills. And finally, I think working alongside a lot of other brilliant minds is very rewarding personally. I know that there's, I think, persons who've worked with NASA before who are part of the partnership or part of Woodside, and you get to meet all these like very like brilliant people in your PhD or doing your PhD project, and that's personally very rewarding for me. So you expand your personal connections and your professional network. I think that's all for me. If there aren't, if there are questions, I'm happy to answer now or later. Thanks very much, Stephan.
I think everyone here would agree that both Vincent and Stephan have displayed an extraordinary depth of knowledge of their particular fields already, and they're very eloquent in how they describe their work. And this is just 6 months or so into their PhDs. So you can imagine how knowledgeable and authoritative they're going to be by the time they've been working on this stuff for 3 years. So they really will be world experts in their space. There will probably be no one else on the planet who knows their stuff as well as they do. And it puts them in that ideal position where they really are an incredibly valuable person in this energy transition, because they know so much about their particular field. So I mean, that's a reason why doing a PhD is so important. Stephan, I'll ask you the same question I asked Vincent then. So how does your typical day proceed, and at the moment, but also maybe in a year or two from now, how do you think it might be looking?
At the moment, I feel there's no typical day for me yet, because I'm still doing some of the coursework. So in my PhD program through the Monash Business School, there's 3 coursework components. One is the philosophy of research, one is quantitative research methods, and one is qualitative research methods. So I'm currently in a course where you have we've got group projects, and you have some kind of examination. So at the moment, I'm more focused on that, but I'm also at the same time still trying to work on a draft research proposal, so that I'm going over journal articles whenever I can, and at the same time through my RA work, whenever there's like another 3 hours or so, trying to catch up with what's happening in the world and writing on that report. So there's no typical day yet. It's because there's so many different things to do. It's a lot of different things, and very exciting.
Yeah, very, very varied. No day is the same. That's great. Okay, we're going to move on to our last speaker, who is Dr. Tanya Tan, who is going to be speaking about some more of the logistic and administrative issues around scholarships. And we have had quite a few questions in the Q&A already, Tanya, asking about, or specifically whether international students are eligible for these scholarships, and a question about due dates. And I just before I hand over to you, Tanya, I should note that today we're talking about the Zema AEMO scholarship and the Woodside scholarships. There are lots and lots of other scholarships available at Monash in the energy space and otherwise. Reisz for CRC is an example of one program that has lots of energy scholarships available, but there are many other avenues for doing PhD. So even if you're not eligible for the Zema or Woodside scholarships, don't let that stop you looking around for other options. So Tanya, I'll hand over to you to talk about how people might be applying for these scholarships. Thank you.
Thank you, Roger. Welcome, everyone. I will actually run through the application process for the Zema and the Woodside scholarships, but I'll also, a lot of the process actually applies to a lot of the other Monash University scholarships as well. So certainly do sort of have a look through the different websites, web links when I do put them up. So today you've heard a lot about the Zema and the Woodside scholarships. These are scholarships for students who are interested in enrolling in the Monash doctoral program, so in the PhD. And the entrance requirements for the PhD is a 4 years bachelor degree in a relevant field, which includes a significant research component or an honours year. So to get into the PhD, it's just a H2A, so an honours H2A or equivalent. However, with scholarships, they are very competitive. So the minimum requirement for scholarships is a H1E. So for Monash University, a H1E is 80% and above, but it's actually based on the qualifications of the institution you attend. So if you attend, if your qualifying degree is from UNSW, then it's what is equivalent at UNSW for a H1E. That is the minimum requirement. For applicants who, where their first language is not English, you do need to meet the English language requirements as well. And this slide does include some information on how you can meet the English language requirements. This information is also available on our website as well, and you can certainly have a look at this information and see which applies to yourself. Now, the most important thing I think is this slide, because there was a lot of questions with regards to deadlines and how to apply. So the first thing you need to do is obviously check your eligibility, ensure that you are eligible for the PhD program. And as I've said, the scholarships are very competitive, therefore a minimum requirement of H1E, that's honours H1 is required. And that applies not just for the Zema and the Woodside scholarships, but also for the Monash University scholarships, for quite a number of the Monash University scholarships. The next step you need to do is basically to find a supervisor. And as you can see on this slide, there is the link to the Monash Energy Institute website, which has a full list of academics who are involved within the different projects within Monash Energy Institute. You are also welcome to pop onto this website down to the bottom here, which is has another link to other academics within Monash University, within all the different faculties, and you can certainly pop on there and have a look at different supervisors and different and their research interests. The process to apply is quite similar within each different faculty. So if you're applying to engineering or BizEco or to IT, you do need to follow these steps. You do need to find a supervisor, and then you do need to submit an expression of interest to the supervisor. The format of the expression of interest is slightly different within the 3 different faculties. So certainly pop onto that web link down the bottom, which will actually have a link to each different faculty's expression of interest process. Now, the expression of interest is pretty much you letting the academic know, or the potential supervisor know, why you're interested in them, in their research project, in their area, what experience you have, what your qualifications are, and if you have a research proposal, then certainly do have a discussion with the academic with regards to your research proposal. I think that was one of the questions in the Q&A and the chat as well, as to whether you need to have a research proposal as well. Once you've located a supervisor and the supervisor has agreed to supervise you, they will issue you, they or the actual faculty graduate research administration team will issue you with an invitation to apply. Once you have received a formal invitation to apply, then you can log onto the system and submit a formal application for admission and scholarship using the online application system. Now, if you're not applying for a scholarship, you can actually apply for a PhD anytime. But if you're applying for a scholarship, you do need to meet the scholarship deadlines. So for the Woodside and Zema scholarships, the scholarship deadline is what we call round 4, which the closing date is the 31st of October. With regards to the Zema and the Woodside scholarships, they are available to domestic students. So international students who are interested in the energy space, you can still apply for Monash, other Monash University scholarships, and you can apply in what we call round 1, which the application closing date closes on the 31st of March. We've actually just closed round 3, which closed on the 31st of August.
The PhD projects are designed to be multidisciplinary. And so you need a topic that crosses over engineering and IT, engineering and business, or business and IT. And you'll need to have supervisors from those faculties on your supervision team to be eligible for the Zema Scholarship. As Sarah discussed in her presentation, we do have 6 projects already described and outlined with existing supervisors. So if your area of interest lies with those projects, they're already good to go, and you don't need to go and chase the supervisors. You don't need to find supervisors. They're there already. You will need to speak to the supervisors and discuss your eligibility and get an invitation to apply through them. And as Tanya said, the Zema and Woodside scholarships are for domestic students, not for international. So you will have to be an Australian resident or citizen to be able to be eligible for those. Okay, so I'm just going to check the chat here, or the Q&A. We haven't had too many questions, which is good. Probably means we're doing a good job of describing everything. So Vishal asks, and this is for me and for you, Paul, as well, if you're able, are there research areas in energy that are based on thermofluids? Are there researchers in Woodside Monash or Monash Energy Institute who work in these areas? Sounds like your area, Paul.
Certainly, if it's thermofluids with respect to high temperature fluids for thermal energy storage, that's absolutely of interest, because energy storage is key to a lot of these carbon transition pathways. If it's thermofluids for other purposes that have to do with energy generation or so on, potentially, I guess it depends on the kind of thermofluids you have in mind. I don't know if that answers the question.
So the trick is, if you've got a particular topic that you're interested in working on, is to go to Monash's webpage, and you can go to the Monash Energy Institute, where there's a list of researchers, or you can search Monash in general looking for an academic with expertise in your space. There's definitely one thing that you need to have is a relevant academic who can supervise the project that you want to work on, and they have to want to supervise you. So if you've got a project you want to work in, do some Google searching on Monash's webpage, and if you can find an appropriate academic who wants to work with you, then you're most of the way there to putting in an application. There's a question about the research proposal that Tanya, I think, did answer. We've got the existing projects that already have project descriptions, but if you want to work with an academic, you will need to have some kind of proposal for a project that you want to work on. Now, what happens in research quite often is that you begin working on a proposed project that looks fine, and you might get 6 months into it, and you might realize that, in fact, the question you're trying to address has already been answered, or it can't be answered for a variety of reasons, and you change tack and you try and answer a different but related question. There's nothing wrong with doing that. It happens in research all the time. Quite often in research, you start working on a problem and you discover something within that problem that is even more fascinating than the original question, and you go down a rabbit hole, so to speak, on that particular part of the problem, and that forms the focus for your PhD, and can be quite different to the original question. Again, nothing wrong with that, but you must start your PhD with a plan. You can't just begin going, I'll work on something or other and we'll just see how it goes. So a proposal for a research plan is necessary at the start. Okay, so we've answered all the questions in the Q&A. I'm just checking the chat now to see if there's anything there. I don't see any questions, just lots of useful information. Paul, Tanya, Stephan, Sarah, Vincent, and Nancy, I'd like to thank you all very much for your contributions to this webinar. I hope this has been very useful for the members of the audience. As we said at the start, doing a PhD is one of the best things you'll ever do if you get the opportunity. And if you do have the grades to get in, I thoroughly recommend it. It will change your life. And I hope those of you who are interested, I wish you all the best with your applications. Thanks, everyone.